Okay, what we need to talk about here today are a couple of formulas. Yeah, we had back, it was at the end of our Calculus 1 class anyway, we did volumes, disk method, washer method. Well, this has nothing to do with that, but it's something like it because one question we can answer with some of the things we've been talking about is how can I determine how long we've done area under curves, but what about, can we determine the length of a curve? And the answer is yes, we can. We can do that. And this, yeah, it does go back to, really goes back to kind of the definition of the derivative. But let's just kind of go through it and see how this all works. And that's why I've got the notes printed off there for you. Or you can get these where you can read them. So determine the length of the curve from A to B. So how long is that? Well, it's a weird looking shape, so I mean I could get my rulers out, I guess, but oh no, don't do this. There it is. Okay. We'll refer to our length there as L, length L. And we're going to use line segments because we do know something about a line segment. We do know the distance between 2 points. So what we can do here is break these up into line segments. Yeah, let's break it up into subintervals, okay? And we can determine the distance here, the distance here, the distance here, and the distance here by distance formula. D equals difference of the y squared, difference of the x squared plus difference of the y squared. That would be distance number 1. So distance number 1, we would take the x's are x sub 0, x sub 1. So x sub 1 minus x sub 0 squared plus the difference of the y, so it would be y sub 0. Y sub 1 minus y sub 0 squared. That would be distance 1, or the length of D1. With me? That's just distance formula. We've done those problems in algebra class. Okay? All right. Whoops, too far. Just want to go to the bottom of that page, I think. Well, D2, D3, D4, very similar, right? D2 would be, oh yeah, I forgot this part. Well, couldn't we refer to that as delta x? And couldn't we refer to that as delta y? It's just a change in y, change in x is all that means. So delta x sub 1 and delta y sub 1. Let's refer to those as that. Makes the notation a little easier. Well, D2, D3, and D4 are same accordingly. And so the length, if we add all those up, sum up the d sub i's, d sub 1, d sub 2, d sub 3, d sub 4, if we add all those up, that's approximately the length of that curve. Now it's a very chopped up curve there, but nonetheless it does an estimation of that. And so replacing, the d sub i's, each d sub I would be delta x sub I squared plus delta y sub squared. You with me? Just kind of replacing some of those things. So I runs 1 to 4. Now, here's the next part. By the mean value theorem. Remember it? Maybe it's been a while. That's been a while. By the mean value theorem, remember what mean value theorem says. If I take a curve, this is not our curve, but if I take a curve there and draw the line between those 2 points, there's some derivative value of c, some c value for which the derivative of c sub I, is equal to the slope. Remember that? There's some C value in this interval, C1 in this case I'm calling it, that matches this slope. That's mean value theorem. We did that way back when. All right, well, the reason I call that to you here is because if I solve this for x sub I, so this is just kind of stating the mean value theorem. Delta y sub 1 over delta x sub 1 is the slope of the line d1, which that's where we're going with this. d1, we're going to use that for delta y1. But anyway, so this is the slope of d1, and then there's some f prime that equals that slope, y sub 1, the slope of that line. So in other words, there's an f prime of c1 that equals the slope of the secant line there, delta x sub I. Okay? Why do I bring that up? Well, let's solve this formula here, whichever one you think. Solve it for delta y. Get delta yi on a side by itself. Delta yi, wouldn't it just multiply both sides by delta xi? You with me? It's just a simple. Multiply both sides by delta x sub I. That gets me this, and that's what I want. Okay? Why do I want that? Well, I'm going to use that and replace delta y. So that can be replaced in any function whatsoever. So there's some function. So here's where I was. So there's some function here. For any function, I can make this substitution. So I'm going to substitute this right here for my delta y sub I. In the delta y sub I. So I'm back to the L approximation here. L was equal to the sum of the delta x sub I squared plus the delta y sub I squared. That was the formula we had a while ago. So now I'm going to substitute this right here for delta y sub I. That's why we went through all that. Okay? Now what? Well, as I note there, can't we factor out delta x sub I squared? Because there's 1 in each one of those. Factor that out, and that leaves me delta x sub I squared times 1. Factor out that, I got 1. And factor it out there, I got f prime c sub I squared. Split that into 2 square roots. In other words, square root that. And what I wind up with, and that's why I wanted to print this out so we can go through this pretty quick, is I wind up with delta x sub I, because delta x sub I squared rooted is delta x sub I, and this. That's going to stay as is. And then I moved it over this right here, because this is an approximation using 4 segments. How could I do better, get a better approximation of my actual length? Do more, right? Do more segments. Do 5 segments. Do 10 segments. Do 50 segments. All right? So I can vary the number of segments. I did 4 here. I could do 50. That would be better. I could do 100. That would be, what would be even better? If I could do infinitely many of them. So let's run in this top number to infinity. So there you go. Do n segments. And so if I could run n to infinity, that would be even better. Matter of fact, that would be exact, wouldn't it? If I could do infinitely many of those segments, that would be exact. Well, what is this right here? That's the integral for. We haven't seen that in a while, but that is the integral definition, isn't it? This stuff right here, n goes to infinity, sum n, 1 to n. That's the integral. The integral from a to b. Notice we've gone from an approximation now to an equals because we're doing infinitely many. But this is just the integral. And I have that integral note. Recall that the definition of an integral is the integral from a to b is the limit as n goes to infinity. Well, all right, so this is what I got. It's the integral from a to b of this. This is my function now, or the thing I use for my length of it. Delta x becomes dx, if you will. This is the formula. All that said, pretty simple, right? Maybe not so simple, but anyway, this will find the length of any curve you want, f prime, That's your curve from A to B. It's square root of 1 plus the derivative now squared, not the function squared, it's the derivative squared, square rooted. So that's the arc length that we're talking about. Arc length equals the integral from A to B, square root of 1 plus the derivative squared dx. And as you can imagine, for a lot of functions, that's going to get fun because you're taking the derivative, then you're squaring it, then you're adding 1 to it, and then you're square rooting it. So it's not going to take very much of a function to get real complicated. So usually the ones that we do for these are really nice. They come out nice. I mean, it doesn't look so nice, but they're going to come out nice because that integral gets pretty hairy pretty quickly. All right, so that's where we'll do that one next. All right, so let me turn this off and we'll do a couple here. Oops. Everything goes dark and everything goes dark. Okay, so now let's go back to that. Yes. Okay. So now, as the one I had there mentioned, what was it? It was find the arc length for y equals x to the 3/2, 0, x to 4. Okay. X is between 0 and 4. And of course, to note there, that's my A and B, right? The A is 0, the B is 4. Okay? So, arc length L, what does it equal? It's equal to the integral of A to B, 0 to 4, 1 plus f prime of x squared dx. So what do I have to do next? I need to do the derivative, yeah. Derivative here, 3/2 x to the 1/2. And that's why it's going to work out nicely. So I put that in for my derivative. So it'd be 1 plus 3/2 x to the 1/2, then square it, dx. And that's what I was telling some of the group earlier. On this test, I will allow a formula card. So this might be when you write upon that formula card there. Might be a good idea. All right. Okay. So what is 3/2 x to the 1/2 squared? Well, that's why we chose that one, because it works out pretty nicely. It would be 3/2 squared would be 9/4. But what about the x squared to the 1/2 squared? That's just x. Square root of x squared is x. dx. So this is my integral. Turns out that one's one of the nicer ones we could run into, because how am I going to do such a one as that? Just use substitution, isn't it? Let u be 1 plus 9/4 x. du then would be, what, 9/4 dx. Divide off the 9/4, which is going to be 4/9 du. Just be the reciprocal there. And so I have the integral be square root of u, 4/9 du. Yeah, that's just now power rule, isn't it? With me? Believe that? Square root of u, 4/9 du. That's just power rule. U to the 1/2. 4/9 u to the 1/2. Which is power rule. So 4/9, add 1, so you have 3/2, so I do 2/3 here. U to the 3/2. Now again, this is a definite integral, 0 to 4, so go back to the x's. It'll be 8/27. Go back to u as x's of 1 plus 9/4 x, and then we'll go 0 to 4. Works out pretty well, especially the 4 part. So if I plug in 4 there, what do I get? 8/27 times 1 plus 9/4 times 4, and then minus 8/27. X works out, well, the X works out good too, real good, because if I plug in X to be 0, that's just 1, isn't it? 1 to the 3/2. What did I happen? I lost some of my notation there, sorry. It's 1 plus 9/4 to the 3/2. Ooh, that would have been bad. Sorry about that. So this, don't forget your 3/2 power there. 1 plus 9/4 X to the 3/2. So this would be, plug in 4, 1 plus 9/4 times 4 to the 3/2, and then 8/27, X is 0, so that's just 1 to the 3/2, so that's just 1. Should have moved up there. The nice thing here about it is that does cancel. Let's go right up here. Get crowded out. All right, so we 8/27. 1 plus, that'd just be 1 plus 9, so that'd be 10 to the 3/2 minus 8/27, which is a pretty good answer. What they would do with that, of course, the 2 means square root, so I've got the square root of 10 cubed. And 10 square root of 10 cubed, 10 square root of 10, isn't it? Because you got square root of 10, square root of 10, square root of 10. Square root of 10, square root of 10 is just 10. So 10 square root of 10. All right, so that's 8/27 times 10 square root of 10 minus 8/27. I'm just working on show you what they would get. So that would be 80/27 square root of 10 minus 8/27. So that arc length, yeah, it's not going to be a nice number, obviously. If you look at it, well, you might think it should be, but it's not going to be a nice number because it's 1 plus the derivative squared, square rooted. That's how you find the arc length. Any question or concern? Okay. All right. Well, let's look at another one here. Okay, how about find the arc length for this one. This one's y equals x cubed over 3 plus 1 over 4x. And we'll go 1's less than or equal to x less than or equal to 3 for A and B. So again, the arc length, part of it is the derivative. And so let's start with finding the derivative. Well, this being, that's 1/3 x cubed, and that's 1/4 x to the minus 1, isn't it? The derivative is, that would work out pretty good. That would just be 1/3 3x squared, and that would be minus 1/4 x to the minus 2, which just works out to be x squared minus 1/4 x to the minus 2. Okay. Turns out that comes out pretty nicely. If you ever figured out to choose this little curve, but it does work out nicely when it, arc lengthwise. But I wanted to show you one how it works out nicely, because it's not just obvious, I don't think. But here it is. So I'm finding the arc length. L equals the integral of a to b, 1 to 3, square root of 1 plus the derivative squared, so this squared, x squared minus 1/4 x to the minus 2 squared, dx. So far, so good? With me so far? All right, well, let's square that out and see what happens. It'd be 1 to 3, square root of 1 plus, okay, what is that squared out? X squared minus 1/4 x to the minus 2 times x squared minus 1/4 x to the minus 2. Well, x squared and x squared would be x to the 4th. Now, this is where it turns out nice. X squared times minus 1/4 x to the minus 2. what does that come out? What happens to the x's? Isn't that 1 over x squared? 1/4. Okay. Minus a fourth. Sorry. And then we have same thing there. Minus 1/4 x to minus 2 times x squared. So that's just minus a fourth again. And then minus 1/4 times minus 1/4 x minus 2 would be plus a 16th x to the minus 4. Well, rearranging a bit here, let's write that x to the fourth first, I think. Yeah, write the x to the fourth first. And the middle, let's go with, well, this and this and this. 1 minus a 4. That's really minus a half, isn't it? So it's 1 minus a half, which is positive a half, plus a 16th. X to the minus 4. And this is where it all comes out nicely. This is why they chose these numbers. Look at this. Watch this. This right here, probably not one you factored before, but that factors. Want to guess? X fourth is easy. That's x to the squared, x squared. And then 1/16 x to the minus 4. Try this. 1/4 x to the minus 2, 1/4 x to the minus 2. Add those up. Pull that out. Get you. So this turns into x squared, factor that out, x squared plus 1/4 x to the minus 2 squared. That's pretty nice, isn't it? So that factors into 1 to 3 square root of x squared plus 1/4 x to the minus 2 squared. They had to choose those real carefully, because now what happens? Square root and the square cancel. We just have x squared plus 1/4 x minus 2 now dx. Okay? Which is just power rules now, right? That's 1/3 x cubed. That's 1/4. What would it be? Minus 1, so it would be 1 over negative 1 x minus 1. 1 to 3. Did I do that right? So it's 1/3. 3 cubed be 27. That would be minus a fourth. 3 to the negative 1 minus, plug in 1, be 1/3 minus a fourth. I believe is right. Which, of course, 3 to the minus 1 is 1/3, so that's 1/12. So this is 9 minus 1/12 minus a third plus a fourth, which works out to be, by my notes anyway, 8 5/6. That one does have a pretty nice arc length.